What if I told you that right now, as you watch this video, astronomers are frantically rewriting textbooks because of a single image that contradicts 13 billion years of cosmic history? In March 2026, the James Webb Space Telescope captured a galaxy that shouldn't exist, one that formed just 400 million years after the Big Bang but contains structures that should have taken at least 5 billion years to develop. This isn't just unexpected, it's the equivalent of finding a modern smartphone in a medieval castle. And the strangest part? This impossible galaxy might force us to completely rethink how the universe itself was born. This discovery defies everything we thought we knew about galactic evolution. The galaxy, designated JWST HD1, contains a supermassive black hole 10 billion times the mass of our Sun, something that should have taken billions of years to form, not mere millions. It shows evidence of complex spiral arms with distinct stellar populations that shouldn't be possible in the early universe. And most baffling of all, it contains elements like gold, platinum, and uranium that we thought could only be created through multiple generations of stars living and dying. It's as if we found a fully formed adult just 1 week after conception. The timeline is so compressed that it breaks our most fundamental models of how galaxies form and evolve. Dr. Elena Rodriguez at NASA's Goddard Space Flight Center puts it bluntly: this single image has created more questions than the last decade of astronomy has answered. To understand how impossible this is, consider that this galaxy existed when the universe was just 3% of its current age, the cosmic equivalent of finding a 40-year-old person when humanity itself was only 1 year old. The structures we're seeing should take billions of years to develop, yet there they are, fully formed when the universe was still in its infancy. How could a galaxy this mature exist so early in cosmic history? And what does it mean for our understanding of the Big Bang itself? To understand why this discovery is so mind-bending, we need to understand what we thought we knew about how galaxies form and evolve. According to our standard model of cosmology, the universe began with the Big Bang approximately 13.8 billion years ago. For the first few 100,000 years, the universe was too hot and dense for atoms to form. As it expanded and cooled, hydrogen and helium atoms emerged, eventually forming the first stars around 100 to 200 million years after the Big Bang. These first stars were massive, burning hot and bright, and had lifespans of just a few million years. When they died in spectacular supernovas, they released heavier elements like carbon and oxygen into the surrounding gas. This enriched material then formed the next generation of stars, which in turn created even heavier elements when they died. This process of stellar birth, life, and death, what astronomers call stellar evolution, is how all the elements heavier than helium were created. Gold, silver, platinum, and uranium can only form in the most extreme stellar explosions or neutron star collisions, which require multiple generations of stars to have lived and died. Similarly, galaxies themselves follow an evolutionary path. The first galaxies were small, irregular collections of stars and gas. Over billions of years, these proto-galaxies merged and grew, eventually forming the structured spiral and elliptical galaxies we see today. Our own Milky Way took over 10 billion years to develop its current spiral structure. Supermassive black holes, which sit at the centers of most large galaxies, also take time to grow. They start as stellar mass black holes, perhaps 10 to 100 times the mass of our Sun, and gradually accumulate more matter. Even with the most aggressive growth models, it should take billions of years for a black hole to reach millions or billions of solar masses. This is where things get strange. Based on everything we know about galaxy formation and evolution, galaxies in the very early universe, say, within the first billion years after the Big Bang, should be small, irregular, and chemically simple. They should contain mostly hydrogen and helium, with very few heavier elements. They shouldn't have well-defined structures like spiral arms. And they certainly shouldn't contain supermassive black holes billions of times more massive than our Sun. Yet JWST HD1, observed just 400 million years after the Big Bang, defies all these expectations. It's as if we found a modern city in ancient Mesopotamia, something so out of place that it forces us to question our entire understanding of history. What I'm about to reveal next is the detailed analysis of this impossible galaxy and the three leading theories that might explain its existence. If you're fascinated by discoveries that challenge our fundamental understanding of the universe, this is exactly why I make these videos. Hit subscribe and enable notifications so you never miss these cosmic revelations as they happen. Trust me, by the end of this video, you'll understand why this single image might completely rewrite the story of our universe's birth. The story of this extraordinary discovery begins on March 12, 2026, when the James Webb Space Telescope was conducting a deep field observation of a seemingly unremarkable region of space in the constellation Eridanus. Dr. Sarah Jameson, lead astronomer for the observation, was the first to notice something unusual in the raw data. Initially, I thought it was an artifact or some kind of interference, recalls Dr. Jameson. The spectral signature showed elements that shouldn't be there in a galaxy at that redshift. I actually spent 3 days trying to prove it was an error before accepting that we might be seeing something real. The redshift of an object tells astronomers how far away it is and, by extension, how far back in time we're seeing it. JWST HD1 has a redshift of Z equals 12.5, placing it just 400 million years after the Big Bang. At this distance, the galaxy should appear as little more than a faint, irregular blob of light. Instead, what the Webb telescope revealed was astonishing. After careful image processing and enhancement, a structured spiral galaxy emerged from the data, something that shouldn't exist for at least another 5 billion years in cosmic history. Dr. James Chen, a galactic evolution specialist at Caltech who was brought in to analyze the data, describes his initial reaction: "I thought it was a joke. I literally asked Sarah if she was playing an April Fool's prank on me. When I realized the data was genuine, I couldn't sleep for 3 days straight." By late March, the discovery had been confirmed by multiple independent analyses. The Webb telescope was immediately redirected to conduct follow-up observations, dedicating over 100 hours of precious observation time to this single object. The follow-up observations only deepened the mystery. Spectroscopic analysis revealed the presence of elements like gold, platinum, and uranium, elements that can only be created through multiple generations of stellar evolution and neutron star mergers. The galaxy's central region showed the unmistakable signature of a supermassive black hole with a mass of approximately 10 billion solar masses, comparable to the largest black holes in the present-day universe. Most baffling of all, the galaxy showed clear evidence of a bar structure and spiral arms, features that take billions of years to develop through the gravitational interactions of billions of stars. Yet here they were, fully formed when the universe was just 3% of its current age. Dr. Elena Rodriguez, who led the spectroscopic analysis, notes, "It's not just one anomalous feature, it's everything about this galaxy. The size, structure, chemical composition, and central black hole all contradict our understanding of galactic evolution. It's as if we found a modern city in the Stone Age." By May 2026, the discovery had sent shockwaves through the astronomical community. Emergency conferences were convened. Research priorities were shifted. The Webb telescope's observation schedule was completely reorganized to focus on finding more examples of these impossible early galaxies. Dr. Michael Patel, director of the Webb Science Institute, describes the impact: "In my 40 years as an astronomer, I've never seen anything like this. We've had paradigm shifts before, but they usually come gradually, as evidence accumulates. This is like having the rug pulled out from under our feet in a single moment." As the scientific community grappled with the implications, 3 main theories emerged to explain the existence of JWST HD1. Each had profound implications for our understanding of the universe, and each required abandoning long-held assumptions about cosmic evolution. The question wasn't just how this galaxy could exist so early in cosmic history, but what it meant for our understanding of the Big Bang itself. As Dr. Chen put it, we're not just rewriting the book on galaxy formation, we might need to reconsider the opening chapter of the universe's story. After months of intensive analysis and theoretical work, scientists have developed three main theories to explain the existence of JWST HD1, each with profound implications for our understanding of the cosmos. The first and most conservative theory proposes that galaxy formation in the early universe could have been dramatically accelerated under certain conditions. Dr. Rodriguez explains, we're exploring the possibility that in certain regions of the early universe, matter density was significantly higher than average, creating cosmic hot spots where galaxy formation and evolution proceeded at an accelerated rate. This theory suggests that while most of the early universe evolved according to our standard models, rare pockets could have experienced time-compressed evolution. In these regions, stars would form and die much more rapidly, black holes would grow at accelerated rates, and galactic structures would develop in millions rather than billions of years. It's like finding a 30-year-old person in a population where everyone else is 3 years old, explains Dr. Chen. It doesn't mean human development as we understand it is wrong, it means this individual experienced some extraordinary conditions that accelerated their development. This theory preserves most of our understanding of cosmic evolution while acknowledging that the process might be more variable than we thought. However, it struggles to explain how even accelerated processes could produce elements like gold and uranium so early in cosmic history. The second theory proposes something far more radical, that JWST HD1 isn't young at all, but is instead a relic from a previous cosmic cycle. Dr. Hiroshi Tanaka at the National Astronomical Observatory of Japan explains, some versions of cyclic universe theory suggest that our Big Bang wasn't the beginning of everything, but rather a transition point in an eternal cycle of expansion and contraction. This theory suggests that JWST HD1 might be a galaxy that survived from a previous cosmic cycle, one that had billions of years to evolve before our Big Bang occurred. While most matter would have been reconfigured during the Big Bang, this galaxy somehow maintained its structure through the transition. It's a bit like finding a fully intact building after a major earthquake, analogizes Dr. Tanaka. While most structures are destroyed and rebuilt, occasionally something survives relatively unchanged. This theory would explain all the anomalous features of JWST HD1, but it requires a complete rethinking of the Big Bang itself, from a beginning point to merely a transition in an eternal cosmic cycle. The third theory is perhaps the most speculative but has gained surprising support in recent months. It suggests that our understanding of cosmic time itself might be flawed. Dr. Sarah Jameson explains, what if time didn't flow uniformly in the early universe? What if, in certain regions, billions of years of evolution could occur within what we measure as millions of years? This theory draws on some aspects of quantum gravity and string theory, which suggest that spacetime itself might have behaved differently under the extreme conditions of the early universe. In certain regions, time might have flowed at different rates, allowing for what appears to us as accelerated evolution. It's like comparing two clocks that tick at different rates, says Dr. Jameson. From our perspective, JWST HD1 evolved impossibly quickly. But from the perspective of that region of spacetime, the evolution might have taken billions of years. What makes these theories so significant is that they don't just explain an astronomical curiosity, they potentially transform our understanding of cosmic history and the nature of the universe itself. If any of these theories prove correct, textbooks will need to be rewritten from the first chapter. As Dr. Patel puts it, we're not just adding a footnote to our understanding of galaxy formation. We're potentially rewriting our understanding of cosmic time, the Big Bang, and the fundamental nature of the universe. All because of one galaxy that refused to follow the rules. Just when you thought you understood the implications of JWST HD1, the story takes another extraordinary turn. In September 2026, 6 months after the initial discovery, the Webb telescope made a follow-up observation that added another layer to this cosmic mystery. Using its most sensitive spectroscopic instruments, Webb detected something that had been missed in the initial observations, isotope ratios that don't match anything we've seen in the present-day universe. Dr. Elena Rodriguez explains the significance. Every element can exist in different forms called isotopes, which have the same number of protons but different numbers of neutrons. The ratio of these isotopes serves as a kind of cosmic fingerprint that tells us about the conditions under which the elements formed. The isotope ratios in JWST HD1 show patterns that don't match our models for stellar nucleosynthesis, the process by which stars create heavier elements. Some isotopes are far more abundant than they should be, while others are mysteriously absent. Dr. James Chen notes, "It's as if these elements were created through processes we don't yet understand." The isotope ratios suggest conditions unlike anything we've observed or theorized, perhaps involving physics beyond our current understanding. This discovery has led to a fourth, even more radical theory, that the fundamental constants of physics might have been different in the early universe or in certain regions of space. Dr. Hiroshi Tanaka explains, "The laws of physics as we understand them depend on certain fundamental constants, things like the strength of gravity, the charge of an electron, or the strength of the nuclear forces. We've always assumed these constants are universal and unchanging. But what if they varied in the early universe or in different regions of space? If the fundamental constants were different in the region where JWST HD1 formed, it could explain both its accelerated evolution and its unusual isotope ratios. Stars might have formed and evolved differently, elements might have been created through alternative pathways, and galactic structures might have developed according to modified physical laws." Adding to the complexity, in October 2026, astronomers discovered that JWST HD1 isn't alone. 4 more galaxies with similar anomalous features have been identified at similar distances, all in the same region of space. Dr. Sarah Jameson explains the implications. Finding one anomalous galaxy could be dismissed as a cosmic fluke. Finding 5 suggests we're looking at a region of the universe that evolved under different rules than the rest. Perhaps most intriguingly, these galaxies appear to be arranged in a pattern that aligns with fluctuations in the cosmic microwave background, the afterglow of the Big Bang itself. This suggests a possible connection between these anomalous galaxies and the very earliest moments of cosmic history. Dr. Michael Patel notes, "We might be seeing the imprint of quantum fluctuations from the first fraction of a second after the Big Bang, fluctuations that somehow led to regions where galaxy formation and evolution proceeded along different pathways." The question now isn't just how these galaxies formed so rapidly, but what they tell us about the fundamental nature of reality. Are the laws of physics truly universal and unchanging? Or do they vary across cosmic time and space in ways we're only beginning to understand? As Dr. Rodriguez puts it, we might be glimpsing not just a new chapter in cosmic history, but a new understanding of reality itself, one where the rules of the game can change depending on when and where you're playing. I genuinely want to know what you think about these extraordinary discoveries. Which of these theories makes the most sense to you? Do you think we're seeing accelerated galaxy evolution, survivors from a previous cosmic cycle, regions with different time flow, or evidence that the fundamental constants of physics can vary? Or perhaps you have your own theory about what might explain these impossible early galaxies. Share your thoughts in the comments below. I read them all and I'm fascinated to see what this community thinks about one of the biggest astronomical mysteries of our time.